Hello, folks. This is probably the last part of this review that I'm going to upload today. It might be the last part that I upload, but I'm going to do my best. I want to cover as much as possible 8, 9, 10, and 11 parts here on this review. And these all deal in some way with indefinite or definite integrals. So that's why I've sort of grouped them in that way. So let's just start simple. This is x cubed plus 3x squared minus x plus 8. And so when they're called antiderivatives for a very good reason. To find an antiderivative of something is to undifferentiate it, is how I tend to think of it. So in this case, the question that's being asked here, what do I have to take the derivative of to get f of x? And now there's a little bit of distinction that I will talk about shortly, and it's the distinction between an antiderivative and an indefinite integral. So I'll get to that when we do integrals, but for now, let's just find a function that we can differentiate and get this polynomial here. So maybe the most natural thing to do is to recognize this as just being the derivative of something. So for instance, I can do this term by term. So let's say the antiderivative of x cubed. Well, what happens when I take the derivative of a power of x? It goes down by 1, right? And the power that it was comes out in front. So if I do this in reverse, which is all I'm being asked to do here really, hopefully it makes sense that I get x to the 4th over 4. And that's the power rule for integrals. That's all integration rules tend to be, is just differentiation rules backwards. When you get to Calc 2, you will learn some clever tricks for doing integrals that the essence of them comes from differentiation run backwards. So like integration by parts, for instance, is the product rule backwards. The log rule is just the chain rule backwards, actually. Or U subs more generally are just the chain rule run backwards. That's how I think of it. So I do this for all the other terms in this polynomial. And I'm going to write this antiderivative with a capital F. That's just kind of tradition when you're talking about the antiderivative of something called f. It's just what we do. So x to the 4th over 4 plus x cubed minus x squared over 2 plus 8x. And I would be well within my rights to stop here. I want to emphasize this because typically when you do an integral, you put a plus c at the end of it. So what is that plus c? We call that the constant of integration. And the point of including it is to make an antiderivative. I got something in my throat. Make an antiderivative into what's called the indefinite integral of this function. And so the indefinite integral is a shorthand for saying a representation of every possible antiderivative of this function. And now you say, how do you determine, how do you represent an infinite class of functions in possibly infinite? We don't necessarily know that they're infinite, but how do you represent all those functions in, a very compact form and write it as a single function? Well, we say plus c, we use an undetermined constant. So that constant could be anything. So the constant tells me which function in that class it is. And you can prove I'm doubtful that it's worth doing, but you can prove if you use the mean value theorem and the fundamental theorem of calculus that any two antiderivatives of the same function can only be different in the constant term. And the reason why is effectively that the derivative of a constant is zero, and it's precisely the constants that have zero derivative. So for instance, if you ever take a multivariable class, you can do an integration in two variables, call those x and y. Then you can integrate with respect to x, and you can integrate with respect to y. But the constant that you end up with when you do such a multivariate integration is typically, so if I integrate with respect to x and I have another independent variable y in that function too, then my constant of integration after having integrated by x will be something with which when I take the x derivative of it, so d dx, whenever I take d dx of it, I get 0. So what that is effectively is a function that depends on variables other than x. In the one variable case, there are no other variables, so they have to be constants. But that's why we write plus c, just in a very short kind of explanation. So okay. So for instance, I could write this polynomial plus 1, this polynomial plus 1,000, this polynomial plus some irrational number, plus pi, plus square root of 2. It doesn't matter, because when I differentiate any of those, whatever the constant was disappears, and I get my original function. All right, cool. Let's move on. I'm going to take these a little bit faster now. So next up, we have square root of x. Immediately, I'm going to note that that's x to the 1/2. And so my antiderivative, I can just use the power rule. So I add 1 to that exponent. 1/2 plus 1 is 3/2. And then I divide by the 3/2. So this is a perfectly acceptable form right here, or you could say 2/3 x to the 3/2. Let me cram a display style in there so it renders right. Oh, it has to be before. I see it's a directive, so it's not parsed all at once. That makes sense. I had actually never tried that before. So either of these forms would be accurate. Again, I could add that constant back. If that's all I'm going to say here. I think there's a few more of these. So I've got f of x equals x to the 1/3. Well, I think I can just say by analogy with the previous problem, display style, I add 1 to 1/3 and I get 4/3 over 4/3, or I could say 3/4 x to the 4/3. So there you go, there's that. And then I think there's an x to the pi. That's kind of funny. But this really drives home. Well, I'll say this. It's easy to prove the when you prove the power rule, typically you prove it for integers. To prove it for any real or integers or fractions are also not so hard to do. But to prove it for any real number, so pi is an irrational number, which means I can't write it as a fraction with integers. It's also transcendental, which means that I can't write it as something like the square root of 2. So I can write down a polynomial equation whose coefficients are integers that square root of 2 makes equal to 0. So in this case, that would be something like x squared minus 2 is 0, right? Square root of 2 solves that equation. It's been proven that no such equation can be written down which pi makes equal to 0. So it's, in a sense, it's even more complicated. It's even more gnarly as a number than square root of 2. The power rule doesn't care. All I have to do is say x to the pi plus 1 over pi plus 1. And I'm just going to leave that there because it doesn't get any simpler than that, really. And then this next one looks like there's a typo here. So let's see. This is 2x times x squared plus 1 to the 100th. The zeros out front were a typesetting mistake. I know because I've done that before. So, okay. This one does not bend so easily to the application of the power rule because of this 2x out front. But what you might notice is, think about undifferentiating it. So one thing you might notice, and this is a very, very common pattern because it's called a U sub, basically, that's all we're doing here. My boyfriend's working on the celery. That's that noise in the background. We're making vegan Cajun food for dinner. It's a party. It always is. So let's see. Think about undifferentiating. So if I were to differentiate x squared plus 1 to some power, then that would act as the power rule does, except then the chain rule would kick in, and I would have to multiply by the derivative of what's inside. In this case, that's the x squared plus 1. The derivative of which is my 2x. So if you like, you could put this in the form of a U sub, but we're going to have plenty of chances to do that later, so I think I'm just going to hold off on that. Equals, so can I say this is x squared plus 1 to the 101 power over 101. Forgot my make fractions look pretty command. And so why has the 2x gone away? Because the 2x would have can't come out when I differentiated this. That's how I knew I could have done it in the first place like this. So when I integrate, so when I undo the process of differentiation, that 2x had better go away. That makes sense, right? If you want to think of it in U sub terminology, 2x would get, U would be what's inside the fraction, and then 2x dx would get absorbed into du. So that's what would happen there. Okay, we're getting close to the one that I want to spend a little bit more time talking about. So there's fx equals sine x. And so I might say, in this case, so my job is to undifferentiate this function. So I might say, what if I integrated it would, or sorry, what if I took its derivative would give me sine x, right? And there isn't an immediate hit in the basic rules, but you would get something like, well, the nearest thing I know is that cosine x has a derivative negative sine x, right? So let me just say this. I'll actually do it right. So put my display style and then my fraction there. And then cosine of x equals negative sine x. So now remember, I'm going to kind of implicitly use the fact here that derivatives are linear. So that means if I take the derivative of 3 times a function, I get 3 times the derivative. Or if I take the sum of the derivative of a plus b, I get the derivative of a plus the derivative of b. They don't really care about addition or about constant multiples. They just kind of pass through the derivative. They get filtered out. It's like they get filtered through, you know? So, so I can say that sine of x equals negative d dx of cosine x. That's just algebra. And then by linearity, I can say that's the derivative of negative cosine. So to sum up, my antiderivative is negative cosine because if I take the derivative of it, I get sine back. Okay. Let's talk about this one. Antiderivative of secant. This one's pretty bad. So when I teach, one of the things that I like to do is I never memorize anything if I can help it. And I don't believe I should hold my students to any higher standard than I hold myself, because that would be wrong. So, well, I have scoured the internet and several journals trying to find a good way of doing this that makes some kind of geometric sense. I haven't found one yet, but and there is one that uses what I would call elementary methods from calculus, but it relies on something called partial fractions, which you're not going to learn until Calc II. So that one is kind of out. So I'm going to show you the standard proof, the one that's in your book, of what the okay, I'm going to skip ahead a little bit, and I'm just going to say, equivalently, we can compute the indefinite integral of secant. So if somehow you got this far without knowing what an indefinite integral is, it's just a collection of all antiderivatives of that function, which is the same in the one variable case as saying it's the antiderivative and then you stick a plus c on the end of it. So here's what I'm going to say. And this looks weird the first and probably the second time you see it. I think I'm starting to get closer to a reason why this is true, but I don't know really how to make it crystal clear and to tell you where this magic step comes from. I'm going to multiply by 1. In a very specific way. So I've multiplied by that and I've divided by that. So these better be up to outside a set of measure 0, the same function. So if I were to multiply this out, I'd get a fraction, and it would be secant squared x plus secant x tangent x dx. And so now you might notice something very peculiar. I have turned this into something for which the top is the derivative of the bottom. So so the secant squared x is the derivative of tangent x, and the secant tangent is the derivative of secant. So long story short, I'm going to take this substitution, u equals secant x plus tangent x. And what's that going to give me? Well, that's going to give me everything else that's in the integral, so secant squared x plus secant x tangent x dx. And then, so my integral becomes straightforwardly integral of du over u. And that's log of absolute value of u plus c. I'm going to say plus c because I used an integral sign to write this. But if I were strictly looking for an antiderivative, so we speak of a antiderivative, but we speak of the indefinite integral because there's many antiderivatives, but there's only one indefinite integral, and that's because it's the collection of all the antiderivatives. There can only be one of those. So if I go back to x's, which is what I have to do after I do a u sub, this becomes secant x plus tangent x plus a constant. And so there's my integral, and there's my antiderivative because I can make this c anything. Heck, I could leave it in, and I think I would still have a valid antiderivative, even though it's not a fully specified function. I would go so far to say it doesn't really matter that much, unless you're being super duper pedantic, then I don't know what the point would be. So that wraps up the antiderivative section. I think the next thing I'm going to set my sights on is this indefinite integral section, but I have some housework I need to do, so I'm going to do that and then handle this page, and then we'll see where we are. All right. Oh, so this is a Stack Overflow, which is kind of the, it's like the internet's help service almost. It's very popular. And it gives you the several different ways to do the integral of secant. And again, the one that I gave you, the multiplying by one method, is the simplest one, and it doesn't involve anything that you don't already know. There's a few clever ways to do it that involve some obscure trig identities and some obscure hyperbolic trig identities, which is another thing entirely. But whatever. All right. So let's see. Stop my share.